Good afternoon, Mawdesley. Pleasure to be back. So yes, this is astrophotography with some emphasis, as you can see in the subtitle there. We're thinking about how you can do some photography of the night sky and objects that are out there in the universe, ideally without using ridiculously expensive equipment, because astrophotography, even more so than conventional daytime photography, can get ridiculously expensive. So I'm going to be starting simple. What do you need to get into astrophotography? Well, basically very little other than a camera and a tripod. I'll be having a think about telescopes and how you mount telescopes, though that won't be the main focus of this particular talk, but just to get everything in context, I'll say a little bit about that. I'll be looking at cameras and how you can do astrophotography, I would argue, about as cheap as you can get, which is a star tracker. I'll explain what a star tracker is in due course. And then, of course, I'll be using this as an excuse to show some of my own images. That's why I come to give talks like this, is to show my images. And I'll finish with, if you did want to take astro photos from the darkest skies possible, one option is to take a safari in Africa where you can get away from streetlights, hundreds of miles away from streetlights, and enjoy the darkest skies possible. So we'll start with what can you do if you've already got a camera, and as I'm talking to a photo group, I will assume that everybody has access to a camera. So if you have a camera, what can you do with basically just a camera and a tripod? Well, one option is just to put the camera on a tripod, point it at the sky, and take an exposure of more than a few seconds. And you'll end up with a picture like this, star trails, as long, again, as you get away from streetlights. This was taken around the mountains of Jordan, so this is not taken from the UK. So because of the rotation of the Earth, all the stars will appear to move during the night, more so than you appreciate. You tend to think of when you look up, everything looks static, but as soon as you start taking pictures, you realize that everything is slowly moving. So this is a pre-digital picture. This was taken quite a while ago, and it was taken, I'll usually give the details down the bottom, and I have handouts, so you don't need to make any notes if you're interested in the actual settings that I use for a particular astrophoto. This was an exposure of about 5 minutes. So the star in the middle there is Polaris, the North Pole star that just happens to be close to where the Earth's axis is pointing. So as the Earth rotates, that star hardly seems to move at all. But as you go further and further away from that particular star, you see more and more evidence of the rotation of the Earth. By the time you're out towards the corners of the photo, you can see there's quite distinct rotation of the entire stellar field. And that amount of star trailing, I worked out what the exposure was. Of course, in pre-digital days, we don't have the information, the metadata for our digital images. So I can't actually remember the exposure, but looking at how much the stars have trailed, I think that was a 5-minute exposure. With digital photography, it's not necessarily convenient to hold the camera open and exposed for a long time to get star trails, but with digital photography, you have the option of taking a whole series of shorter exposures if you wanted to. Okay, that generates quite a lot of images on your SD card, but what the hell, if you've got a 1 terabyte SD card, you can store as many images as you like, so it doesn't really matter. And unlike taking pictures on film, you're not thinking about the expense of each picture, each frame that you're taking. So with digital photography, you can take much longer exposures. So in this particular case, 6 hours. You can tell it's 6 hours because each star trail is approximately 1/4 of a rotation. So the Earth has turned 1/4 of a rotation. So I didn't take a single 6-hour exposure. What I did was set the camera to take a whole set of 1-minute exposures and just left it running whilst I went away and did something else. It looks a little bit like daylight. We seem to have these observatory domes that appear to be in sunlight, and we appear to have some colored foreground and a blue sky. But actually, it was a relatively dark sky, but there was a full moon out. And so with the full moon, it does tend to produce a little bit of blue in the sky, and a full moon will quite definitely illuminate the foreground and illuminate, in this case, the white domes of this particular observatory. But in addition to taking a whole load of images and then asking some software, put them all together for me, there's free software that will do that for you. You don't have to worry about how to do that. Just take a whole load of individual frames, throw it at the software produces that. As an option, the software will also stitch them together into a movie, and then you can watch the stars rotate around the North Pole. There's the North Pole. This is taken from the island of Tenerife, so the pole star is rather lower in the sky than it is from England, but you can see the individual stars rotating around the pole star. And if you've taken 6 hours, again, you will end up with a movie in which the stars move and end up making 1/4 of a rotation. Of course, if you decide to expose for less time, you get shorter star trails. So that's one advantage of digital photography, is you can play around with the result, unlike with film, where you have to really think ahead as to what it is that you want to photograph. In some cases, you simply have to be in the right place at the right time. So although technically speaking, this is not nighttime photography, I thought I'd include it anyway. If you want to get a total eclipse of the sun, of course, you have to figure out when and where on the Earth do I have to be to get myself lined up perfectly so that the disk of the moon exactly covers the disk of the sun. That only happens once in a while, maybe once a year, but you have to be in the right place on Earth to actually witness that. So in this particular case, my friends and I decided that we would like to experience a total eclipse of the sun at least once in our lives, and we chose to go somewhere that is unlikely to have cloud. We went to the Sahara Desert because the track was going through Africa. It went through the Sahara Desert. We figured it's not likely to be very cloudy in that particular location, so that's where we decided to catch this back in 2006. What you see when the moon covers the sun is the sun's corona, the outer atmosphere, and that will change in a long 11-year cycle depending on how active the sun is, how much is going on the sun, how many eruptions and flares there are on the sun. And at the moment, the sun is quite active, which is why we've been getting aurora recently. So this wasn't recent aurora. This was from a few years back, and again, this was pre-digital, so this is taken with slide film on a Nikon FM2. But it gives you an idea of what you can expect the northern lights to look like if you go to the Arctic. So this happened to be Iceland, but if you go to Scandinavia or Alaska or other northerly latitudes to see the aurora borealis, or of course southern latitudes to see the aurora australis. So when the aurora decide to hit, it can be absolutely spectacular. The entire sky was lit up, and you get these beautiful curtains of light that seem to be just hanging in the sky, even though they are hundreds of kilometers high. And the light is what you don't get in a static image like this, is you don't realize that there is a shimmering quality to these curtains of light. And basically, you see ripples running up and down the curtains as they hang in the sky. In this particular case, this is looking in a slightly different direction. For those who know the sky, perhaps you recognize the constellation of Orion just peeking in on the left-hand side there, and the Seven Sisters star cluster in the middle. But on this visit to Iceland, we were lucky enough to see essentially the entire sky light up for quite a few hours. This was Fujichrome film with a wide-angle lens, a 24mm lens, and a few minutes exposure. Again, a few minutes exposure with slide film, but with digital photography, you don't need to expose for as long. And of course, I'm sure you're aware that recently the sun was so active that these aurora were actually visible from the UK. As far as I know, nobody saw quite the same sort of structure of curtains and arcs and folds and rays that we saw in the Arctic, but it's still possible to capture some of the auroral colors. In this case, just before I went to bed, I literally just got out my iPhone, held it on the windowsill, so this is not a tripod, this is just an iPhone sitting on the windowsill pointing out of my north-facing bedroom window. And although I could barely make out what was going on by eye, there was very little to see, but clearly the camera does pick up a little bit of the green and the red of this particular auroral display. Did vary from different parts of the country, but I thought it was interesting that the quality of cameras in phones these days is getting so good. This would not have been possible 10 years ago because the technology that was typical inside a phone just wasn't up to the job of taking a low noise, a relatively low noise picture of the night sky and reasonably faithfully reproducing the colors. Remember that your eye doesn't see these colors simply because the cones, the photoreceptors in your eye, are not sensitive to low light, and so you don't tend to see the colors even though the camera does pick them up. Another recent development is not only the fact that we saw aurora fairly recently, and probably will continue to see aurora because the sun is very active, so I would imagine throughout the winter we are likely to see aurora even coming down to the UK latitudes. But just in the last week or two, we've had a visitor, this comet, which goes under the wonderful name of Shushanshan Atlas, or Comet 2023A3, for those that prefer that. So this was taken now we're talking back to digital again. This was a standard kit lens, and I just took a series of 4-second exposures. I wasn't sure what the exposure ought to be. I took 4 seconds because this is a camera sitting on a tripod, and if I took longer exposures, the stars would have moved. Like we saw earlier, we would have got star trails. So I took a series of short exposures and then added them all together. Again, there is free software available to add these things together if you take a series of short exposures.
What aperture do you use?
In this particular, usually full open. It depends on the quality of the lens. When I was a lad, I always used to stop the lenses down, but that's because I used cheap lenses because I couldn't afford decent ones. If I'm using a Nikon lens on a Nikon camera, in general, I will open up. Because if you're doing night photography, and especially if you're looking at very faint objects, you need every photon you can get. And so the idea of stopping down, I appreciate you might want to stop down if it improves the quality of the image, but hopefully, if you can get lenses that don't require that, then you can catch all the light. It's a shame that all of this light is trying to get at your camera. It's a shame if you throw 3/4 of it away by stopping the lens down, but I appreciate sometimes you might have to. The test, of course, is to see, are the stars sharp in the corner? If you take an image and everything looks fine in the middle, but it looks a bit ropey at the corners, then you've got some aberration in the lens, and that might benefit from stopping down a little bit. But in general, all of the images I'm showing you are taken at full aperture. And in this particular case, the tail of the comet is pointing away from the sun. This was taken in the evening, so the sun has set down below the horizon, down in this bottom right corner, and the tail is being blown back behind the comet. It's not an indication of which direction the comet is traveling. The comet is not traveling from top left to bottom right. The comet is actually traveling that way. In other words, tail first. The tail doesn't simply flow behind the comet as it moves. The tail is blasted away by radiation from the sun. And the comet is now moving in this particular direction, top left, and it's getting higher in the sky, which means that you can see it for longer after sunset. But unfortunately, as it gets further and further from the sun, given the sun is evaporating the ices which produce the tail, as it gets further from the sun, the comet gets a shorter and dimmer tail. So it's a trade-off between getting higher into a dark sky versus the comet getting dimmer. So I think it's pretty much past its best now. And that was about as good as I could get, unfortunately, on the night of Storm Ashley, where I was trying to photograph this thing in a howling gale, but I thought it was worth a go because I wasn't confident that I'd have clear skies for the next few days thereafter. So there's a fair bit you can do just by putting a camera on a tripod. Done deal. Keep the exposures short to avoid the stars moving. If you want the stars to move, great. Take as long an exposure as you like. If you don't want the stars to move, keep the exposures to just a few seconds. So what about if you did decide that you did want to buy some ridiculously expensive equipment and get into astrophotography seriously? What if you wanted to buy a telescope and put the telescope on some sort of a mount? Generally speaking, there will always need to be a serious mount because the Earth will always rotate. It's a bit of a pain, but yes, the Earth is always rotating, and therefore every object in the sky will appear to move with 1 revolution per day, and if you don't want that to blur your images, you have to think about how you're going to move your telescope or your telescope and camera to compensate for the rotation of the Earth. One option, of course, is you use a telescope above the Earth, and the Hubble Space Telescope was launched in 1990, so it's an old man now. It's 34 years old. So watch out on eBay, because eventually they are going to try and get rid of it. It's not going to last forever. Hopefully it's good for a few more years. When they built it in when they launched it in 1990, they were hoping that it would indeed last for a few decades. The fact that it's still producing fantastic images 34 years later is a testament to the amount of engineering and design that went into a beastie like this. It's not going to last forever, so if you did want a billion-dollar telescope, it of course is capable of producing fantastic images of galaxies and nebulae within our own universe, either next door, this galaxy is not that far away, or within our own galaxy, this Pillars of Creation is a stellar nursery where stars are being born in the tops of these pillars here. So yes, you can get some fantastic images if you've got $1 billion or so to spare. If you haven't got $1 billion, I'm assuming that might apply to all of you, yeah, okay. There are cheaper ways of doing it. If you've only got 100 million, if you're really that strapped for cash that you only have 100 million, there's a 747 with a telescope in the back cargo bay here. It's called SOFIA, the Stratospheric Observatory for Infrared Astronomy. There's an infrared telescope in the back, and they open up this hatch to take pictures of the sky. They put it in an aircraft because an aircraft can get above quite a bit of the atmosphere. Hubble, of course, is above the atmosphere, essentially. This isn't above the atmosphere, but it's fairly high in the atmosphere, which means a lot of infrared light is not absorbed, and hence they can do a lot of infrared astronomy using this particular beastie. But now the James Webb Space Telescope, which is also an infrared telescope, now that that is placed at a particular position that will allow it to see the universe, basically NASA have decided they no longer really need this facility. So again, this will be up for grabs. I haven't seen it on eBay yet. That was its original cost. I'm sure it'll be less than that when it goes on eBay, so just watch out for it. If you've only got £1 million or so, then there are other telescopes. For instance, the Liverpool telescope, which is sitting on the island of La Palma. The Liverpool telescope is the world's largest robotic telescope, so there's no people operating it. It's entirely operated robotically, and it can produce some superb images. But you don't have to buy one of these robotic telescopes for yourself. Because they're robotic, they can in principle be operated from anywhere in the world, and Liverpool and other institutions make time available on these robotic telescopes. Some of them are a little bit smaller than the Liverpool telescope, but still they are quite massive by amateur standards, and you don't have to buy them, you can basically just rent them. If you just want to use them for an hour or two, you can effectively buy time on telescopes either in the Canary Islands or in Australia. It has the advantage that you can do your astronomy during the day whilst it's dark in Australia. So for a modest sum of, I'm not sure quite how much, a few tens of pounds, you can basically buy time on telescopes and take images from all sorts of places, South America, Australia, etc. Amateur astronomers would prefer to have a telescope in their back garden, so it's their telescope and they have total access to it. But things can get quite complicated. When you say to yourself, well, I'm interested in sort of doing some astrophotography, I quite like the idea of buying a telescope and taking pictures of these objects that I've seen in magazines or on Sky at Night or in Brian Cox interviews or something. I'm quite interested in buying a telescope for myself. It gets very confusing because there are so many to choose from. You might think it's complicated just deciding which camera are you going to buy. With telescopes, it's 10 times worse because there are so many manufacturers of telescopes and the telescope types are many and varied. So some people will decide to buy themselves a telescope and then turn it into spaghetti by deciding that they really want to add this accessory and that accessory, and they want to add this and then add a camera and then add this and then add another box. Some people love the idea of just basically getting involved in the technology side of how am I going to get this telescope to do all of these wonderful things. Other people don't care about the technology, they just want to either look through a telescope at all of these beautiful objects or find the simplest way possible of imaging. But some people love the idea of it's not just a telescope, it's the start of a hobby which could end up with all sorts of things getting bolted on to the original telescope in order to extend its functionality. When thinking about, I want to photograph, I don't know, a distant galaxy or a comet or this or that, It's tempting to think that the important thing is the quality of the optics, because of course as photographers you know that when you're photographing a particular object, what matters probably more than anything, apart from the eye of the photographer, is the quality of the optics. If the quality of the optics is rubbish, then you're not going to get a particularly good image of the object that you're interested in. So you might think the most important thing, if you're deciding on, I'm going to buy a telescope because I want to photograph distant objects in the universe, it's tempting to think that the most important thing is the quality of the optics. But for astrophotography, it is argued, and I guess I'd probably agree, that it's the quality of the mount on which you put the telescope that really matters. So this is a very massive mount. Is it worth $10,000? Well, that's up to the individual to decide how deep their pockets are. The more expensive the mount, the more stable it is, and the more accurately it will then move the telescope to track the stars as they appear to move. In other words, compensate for the Earth's rotation. If you don't get that right, then it doesn't matter how good your telescope is. Your telescope might be a superb telescope costing many, many thousands of pounds. But if it's not following the object you want to photograph, then your object is going to get blurred, even though you've got a good quality set of optics. So many people say, spend serious time thinking about what mount you're going to put your telescope on, or your camera system, or whatever it is. Because if you get that wrong, you can easily end up with a white elephant of a fantastic telescope, but if it's not on a nice stable mounting that can move and accurately follow the sky, then you're not going to get the astrophotos that you want. I'm not going to talk about how you decide on which telescope to buy, but if anybody has any inkling of being interested in buying a telescope, either for themselves, for astrophotography, or for another member of the family, for a youngster that's interested perhaps, I would suggest you have a quick chat to me and I'll give you some information as to how you go about making that decision. So I'm not talking about that this afternoon, but I've got a separate talk about a sort of rough guide to how you think about deciding how to buy a telescope. If you do decide to get a telescope, the second choice is, what are you going to do with it? Is it going to stay indoors and you take it outside into the garden whenever you want to use it? Or do you have yourself a back garden observatory, which a lot of amateur astronomers would like to have? Now, that's not exactly a back garden observatory. That's a professional observatory, Mount Palomar in California. It's a fantastic place. It housed the world's largest telescope. It was the largest telescope in the world when I was born. It was the largest telescope in the world for my childhood. It was the largest telescope in the world for most of my adult life. So I decided I really wanted to visit it. So in 1982, as a student, I visited this particular location in California. Looks like I'm wearing the same shirt as I had on in 1982, but that's not that unusual. When I went there, I thought, that's fantastic. It's a really big telescope, really impressive, nice place in California. When I grow up, I'm going to have an observatory like that in my back garden. I had to downside my ideas slightly, so what I actually ended up with is a shed from B&Q that was converted into an observatory. So that was when, 1998, I took that after I'd moved into this particular house. But at least it meant I could have my telescope in my back garden in a shed such that I could enjoy the sky. You can tell this is a very old picture because A, the observatory is clean and there's no sign of any spiders or cobwebs in there, and B, the laptop looks like a brick in the background there rather than these tiny thin laptops that you get these days. But that was my telescope that I had, what was it, a quarter of a century ago now. And if you do decide to buy yourself a telescope, then you can get some wonderful images, both eyeballing as well as astrophotography. Even something as simple as deciding that you want to look at the moon. That might seem a little bit pedestrian. If you've got the entire universe to discover, why would you only look at your nearest neighbor? But simply looking at the craters and mountains on the surface of the moon, as the month progresses, the shadows change as the angle of the moon relative to the sun changes. And when you start looking in detail, this is with my Nikon camera on the back end of a relatively large telescope. And at this scale, it's difficult to see just how much detail there is in the image, so I've simply blown up part of it so you can see it a little more clearly. You can see individual craters clearly. You can see where the sun is just catching this particular sort of semicircular bay in this lunar sea. It's basically a lava sea, if you want to think of it that way, a basalt sea. You can see mountain ranges, you can see lots of craters. If I just show you what the bottom half of the image looks like, that's the crater Copernicus. You can see all sorts of detail. And this is visible by eye, as well as, in this particular case, there was no particular fancy processing. This was just bolt a Nikon camera onto the back of the telescope, hit the shutter button, that's what you get. So with a large enough telescope, a large enough, unfortunately, expensive telescope, you can get absolutely superb images of bright objects like the moon. Of course, if you want to get very distant, faint objects, then you have to worry about longer exposures. But at least with something like the moon, you don't have to worry about how much light there is, because if it's a big telescope, this particular telescope has got a front element that is 14 inches in diameter, so you can imagine how much light is collected by that. The more light you collect, the easier it is to snap short exposure images.
What's the focal length of that?
That particular beastie was 3 meters. And with that telescope, this was when we had taken some students. The universities of Liverpool take students out to the Canary Islands to give them an experience of what a dark sky is actually like. And lucky enough, when the students were busy with something else, again, I purloined it for a little while, stuck my Nikon on the back and took a few images. So perhaps if you've ever seen these things, you might recognize the pillars of creation. So this is the star-forming region as imaged by Hubble that I just decided to have a crack at. There's another nebula in this particular case. This is a sort of forward look as to what the sun will look like. Eventually, the sun, towards the end of its life, in a few billion years' time, the outer atmosphere of the sun will get sloughed away and will produce a nebula like this, and the tiny little dot that's left is the core of the sun, the core of this particular star. So this star is very similar to our sun, and this is what our sun will look like in a few billion years' time. One thing to note is that these colors are all natural. None of this is false color. This is the actual color as recorded by a color camera, and as close as I could get it to the true colors that were existing at the time. In other words, things in the sky are genuinely colorful. When you go out at night and look up and you see white dots on a dark background, you tend to think, well, all stars are white and there's no color up there. But actually, the universe is very colorful. And if only you can collect enough light or expose for long enough, if you've got a smaller telescope, you might have to expose for longer. Again, the importance of getting the tracking right. But the color is there, and you can pick this up in color cameras. In some cases, the color contrasts are beautiful. This particular nebula has got some blue and some pink because there's different physics going on. In one case, it's how light is scattered. In the other case, it's how light is emitted from certain atoms. So we're not going to go into the detail, but these colors are real color differences which contain, in principle, scientific information. But I take these pictures just because I think they look really cool. As well as taking pictures of the night sky, again, I'm talking about the night sky, not the day sky, but I may as well at least say that it is possible to spend money on really expensive equipment and take pictures of the sun. I hope you're all serious enough to realize that you never look at the sun, you never look at the sun naked eye, you never look at the sun with binoculars, you never look at the sun or attempt to photograph the sun unless you have the very specific equipment which is designed to let you see features on the sun. So this was taken with a solar telescope, which unfortunately definitely falls into the category of ridiculously expensive equipment, because you really can't buy solar telescopes for just a few £100. You have to spend over £1,000 to give you the sort of equipment that allows you to safely take pictures of the sun. So the sun had a number of sunspots on it, but what was quite interesting is that we get these prominences, these huge eruptions on the surface of the sun. Some of those may well be responsible, for instance, for the aurora that we've been seeing for the last few months. It's eruptions like that that we see on the edge that throw material out into space. If it happens to come towards the Earth, this material hits the Earth's atmosphere and makes the atoms in the Earth's atmosphere glow. That's what an aurora is. It's the glowing oxygen and nitrogen because of stuff thrown out from the surface of the sun. So that's a little bit of an aside, because that's a daylight picture, not a nighttime picture, but just another reminder, don't attempt to do that unless you've got the right equipment. So let's have a think about cameras. I've said a little bit about telescopes. Let's have a think about cameras and how you might try and get the cost down by taking pictures of very distant objects, but without spending tens of thousands of pounds on expensive telescopes. A reminder, you know all this because you're a photo group, but a reminder that if you have monochromatic film or a CCD, a charge coupled device chip, in other words, a digital acquisition chip, then if you're focusing light onto that, you get a monochromatic image with black and white film, or if you're using a standard CCD chip. If you want to get a color image, well, one option is before the light hits the black and white film or the CCD chip, you put in a colored filter. You take an image through a red filter, then an image through a green filter, then an image through a blue filter. That gives you 3 images, and those 3 colors, those 3 images, red, green, and blue, can be combined together in a computer to give you a color image. Now, of course, after black and white photography, some clever person figured out that actually you can put the filters in the film emulsion themselves, and you can get color print and color slide film by effectively embedding the color filters, not putting them in between the lens and the film, but embedding them in the film. With digital photography these days, it's not quite the same because there's no such thing as a color CCD. CCDs are sensitive to all colors of light. So if you want to actually make a digital color camera using a CCD, you put the filters on top of the actual chip itself. In other words, if you were to look at a CCD chip and look in detail at what's going on in there, you find a grid of pixels that have been placed with colored filters, usually red, green, green, and blue. There are 2 greens, partly because it's a lot easier to arrange them in squares, and so with squares you have 4 filters, even though in principle you only need 3, red, green, and blue. So they double up on the green. That also has the advantages that because human vision is more sensitive in the green than it is in the red and the blue, it gives you a better color balance as well. So there are red and green and blue filters on top of individual pixels, and the computer in your camera knows which pixel has got which particular colored filter on top of it. And so the so-called Bayer grid leads to the computer knowing that if I take these pixels, I get the red part of the information. If I take these pixels, I get the green. If I take these pixels, I get the blue. And the computer will then say, I've now got a red, green, and blue image. I can combine them together and generate a color image, and I will slap that on the SD card for your convenience. And that's how it generates a color image. So it's still black and white photography, as it were, but with colored filters, and the digital revolution simply means that that's all done for you rather than you having to put in a red and a green and a blue filter and generate 3 images which you combine again later. If you want to do that with astrophotography, you still have the choice of saying, well, you can buy cameras that are optimized for astrophotography. For instance, you can get a little color camera that's 2 million pixels or so, and it's the sort of camera that you would use to replace the eyepiece on your telescope. Instead of buying a telescope with an eyepiece and looking through it, you can replace that eyeballing eyepiece with effectively an electronic eyepiece, if you want to think of it that way, which is a small color camera about the size of a 35mm canister, and that would give you color images, and that will cost you of order a few £100s. If you were serious about astrophotography, you might want to get dedicated astro cameras that have more pixels in them. For instance, a 7 megapixel color camera could cost anything up to £2,000 or more. But what is perhaps surprising is that the same manufacturer might actually make a 7 megapixel mono camera, and look at the price. Exactly the same. As far as the manufacturers are concerned, manufacturing a color camera and manufacturing a mono camera, there is virtually no difference between the two. The technology is identical, except that in one case, the Bayer grid of filters is not placed on top of the chip. That is such a trivial thing to do when manufacturing that whether you put the Bayer grid there or not doesn't make any difference to the cost. The cost is determined by how many people want to buy this camera and how many people want to buy that camera. And if the number that want to buy the two is similar, they get sold for similar costs. So mono cameras and color cameras aren't necessarily that different in price. But if you wanted to buy yourself a mono camera, and then you say, well, I've got a mono camera, but I want to take color images, then you would need to go back to what I said earlier. You would then need to put red and green and blue filters in between where the light is gathered and the camera itself. And that would often be done with one of these, a so-called filter wheel. In other words, a wheel that contains various colored filters, and this would rotate, usually on computer command, into position to put a particular filter in between the light path of the telescope and the camera itself. In other words, you would often take a laptop, plug it into the camera, and the laptop would say, I want to take a picture of 5 minutes exposure and I want to put a red filter in place. And the computer would send a command to this filter wheel, which would rotate until the red filter came into the right position. And then I now want to take a 5 minutes blue and a 5 minutes in green. And quite often this would be automated, so it would just get on and do it whilst you go inside and watch Match of the Day. But of course, what I'm talking about is not spending huge amounts of money on dedicated astronomical cameras, although some people prefer to go that route. My preferred route for many a long year now has been, well, I've already got a camera. I've got a digital SLR, or in some cases it might be a bridge camera, or it might be a mirrorless camera. It doesn't really matter what type of camera it is. If you've already got a camera which serves you well for daylight photography, you don't need to go out and buy yourself a dedicated astro camera at the expense of hundreds, if not thousands, or many thousands of pounds thereafter. So what I'm talking about for the rest of this particular talk is, if you've already got a camera, what can you do with Astrophotographer with the camera that you've already got? And remember, the only thing you need to worry about is the fact that the Earth is rotating. And therefore, if you want to take an exposure of more than just a few seconds, you have to worry about the Earth's rotation. So you have to find some way of counteracting the Earth's rotation by moving the camera at a revolution speed of 1 revolution per day in the opposite direction. And I decided a few years ago I would simply build myself one of these, a so-called tracker, a star tracker. It's basically a couple of hinges, a bit of aluminium, a motor on the bottom, a couple of batteries and a potentiometer, such that when this motor turns, it lifts this arm and it basically rotates the camera at the revolution rate of 1 revolution per day. In other words, I just made sure I ran that motor at the right speed to give me exactly the right rotation speed. You can build yourself a tracker like this for a few pounds, maybe £10, £20, something like that. I have instructions here if anybody's interested in building one for themselves. So that's what I mean about astrophotography on the cheap. If you've already got a camera, a tracker only costs a few tens of pounds at most if you wanted to build one for yourself. You can go out and buy one, that's fine. So I built one myself, used that for many years, and then I decided sometime later I would try out one of these commercial packages, one of these commercial trackers. It's a white box, and the camera gets bolted on as it would on a tripod head. You would often put this on the tripod and then bolt the camera onto the 3/8 or 1/4 inch width at the top there. This little telescope on the side is a little sighting telescope that allows you to make sure that you've got the axis of rotation of this star tracker aligned with the axis of rotation of the Earth. If the Earth's turning one way, you want the tracker to be lined up on the same axis, rotating in the opposite direction. What's inside a star tracker? It's basically just a motor in a box. They can be quite expensive considering that they are just a motor in a box, but you're paying for the precision, the stability of the system, and the precision of the motor and gearbox and worm wheel driven from some electronics which is fed from battery. The Earth actually rotates 1 revolution in 23 hours and 56 minutes, and these things are designed to turn exactly in 1 revolution in 23 hours and 56 minutes. In other words, they are timed very accurately to be the same as the rotation rate of the Earth. And that's why you might pay £100 or £200 for a box like that. But that's how you would use it. You would stick your tracker, your white box, on a tripod, usually, doesn't have to be, but usually, and then you would put your camera, sometimes on a ball and socket joint, such that regardless of the fact that your tracker is now lined up with the Earth, your camera can point in any direction you like. You're not restricted to taking a particular part of the sky. Once the tracker is set up, you can move your camera to look wherever you like if you've got a little ball and socket joint on the top there. This is how I've often used it in the past. There's my Nikon. That's the longest telephoto I've ever used on a star tracker. That's the 300mm lens. And I put it onto a little mount which allows me to move the camera in any direction regardless of the tracker orientation. That 300mm lens, I hope you recognize, is exactly what I was talking about last time I was here. I like taking wildlife photography images. My camera and lens of choice at the moment are a Nikon 7500 and a 300mm f4 lens. That's the size of the telephoto lens. I like that size lens because it is relatively lightweight, not that large, and if I want to take it to Africa to take pictures of lions, like that one on the left-hand side, it doesn't add that much to my luggage or my gadget bag, etc. It's a relatively compact but very useful focal length. 300mm is as long as I ever need when I'm on safari taking pictures of lions or zebras or giraffes or anything else. And as it happens, that also is about the lens focal length that I like to use for astrophotography. So if I go to safari, I generally don't take a whole shed load of lenses. That one does for most things. Maybe that and a wide-angle lens. That's pretty much all I need. So let me show you some of the images I've taken. So I've now pushed aside the ridiculously expensive equipment. I'm talking about the equipment that I would have anyway if you're taking pictures in daylight, whether it be of your kids or of weddings or of lions or zebras or anything else. And what you can do with a star tracker, which costs almost nothing if you build one yourself and might cost you £100 or more if you decide to buy one. So these are examples of pictures that I've taken with my DSLR and a tracker. You're not limited to just taking pictures of bright objects like the moon. You can take pictures of faint objects, including some really faint objects, which I'm going to come to in just a moment. So yes, if you want to buy yourself an expensive equipment like a telescope, you can do that. And I have seen some superb images taken by expensive equipment like expensive telescopes on expensive mounts, possibly with expensive cameras, and they produce stunning images that a little while ago would have been inconceivable. Technology has moved on so much in the last 10, 20 years or so. Things that could only have been done by professional observatories in the past can now be done by people in their back garden, as long as they're prepared to spend a few £1,000s. It can be incredible, it can be incredibly rewarding, but just a warning, to get the most out of astrophotography with big telescopes and big mounts in observatories, it will take time, it will take effort, and quite definitely it will take cash. So let me show you what you can do with a little bit of time, but very little in the way of separate cash. When it comes to taking pictures, what you see on the back of your camera is not what ends up on the web page or in a magazine or whatever. If you take a picture of the sky, especially in a light polluted part of, I think this was Birmingham, I can't remember, what you often see when you look on the back of the camera is, oh God, that looks horrible, because you will often pick up a whole load of the effects of scattered street lights as well as the interesting object that you're trying to photograph. So this is a picture taken with a 300mm lens, and you can hardly see what's going on if you look on the back of the camera. That's what a raw image would look like. But there's plenty of software that will help you figure out, well, the sky shouldn't be orange. That's just the effect of street lights. Let's take the brightness of the sky down a bit, and let's try and bring out all of the detail in this nebula. Just happens to be called the North American Nebula for reasons I hope you can just about recognize, this particular nebula. So from images like that, they can be processed to make the sky darker and a little bit less orangey and bring out the colors and the structure and the beauty of these nebula and other astronomical objects that you may be interested in. So it can't deal with absolutely terrible light pollution, but even though it looks bad, you can still use software to mitigate some of the impact of light pollution. Better still, get away from the light pollution. But even if you've got some, that doesn't mean you can't do astrophotography. People have done wonderful astrophotography even from the middle of a city because of the software tools at your disposal and to some extent because of filters that allow you to get rid of street lights. Again, I'm not going to say much about that, but happy to cover that in Q&A afterwards if you so wish. So a 300mm lens shows a stellar nursery. This is a nebula that's seen in the winter skies. I took this again, I think, from Birmingham rather than from Liverpool. And this is a place where stars are being born. A large cloud of hydrogen is collapsing. The colors, again, are genuine. Hydrogen tends to glow red on the whole. And this is a stellar nursery where a large cloud of hydrogen is slowly contracting and stars are being born right in the center there. At the opposite end of their lives, some stars will die, and this is the Carina Nebula, visible from the southern hemisphere, so this was taken on safari rather than from the UK. But this is a star that's coming to the end of its life, unlike the previous one, which was a stellar nursery at the start of its life. This star is very unstable. They've been watching this star for a while, and for possibly thousands of years, it's been shrugging off lots of its outer atmosphere, which is what this nebula is. This pink nebula, this flower-like thing, is the outer part of this star that's been shrugged off probably thousands of years ago and is now hanging around as this nebula. The star itself is embedded right in the middle there. This star is so unstable, they think this is a candidate for a star that's going to go supernova before too long. That doesn't mean tomorrow or next week or next month. It means it could be thousands of years, but it could be that the next star that we see go supernova could be this one. And astronomers are watching this one because it's such an interesting object because of all of the nebula that's been generated up to this point. Some stars have already exploded. This is one that exploded 15,000 years ago, and we don't know which particular dot it used to be, but perhaps there's nothing there now. But effectively, this star went supernova and blew out what is now a large bubble, or shell, if you like. And here we can see the edges of the bubble. Just like when you look at a soap bubble, you tend to see the edges. You don't necessarily see anything if you look into the soap bubble as it's transparent, but you often see a little bit of the shape of the soap bubble around the edges, and that's pretty much the same thing. So although it might look a bit odd, this is probably spherical, and we're just looking at it and we're seeing a bright shock wave on the left-hand side and a bright shock wave on the right-hand side. Fortuitously, there happens to be a star there, but that's not related to the supernova in any way. Again, these colors are genuine. This is genuinely pink and blue. That tells us that this particular object is actually made of hydrogen, which is glowing pink, and oxygen, which is glowing blue. So the colors aren't just pretty. They're actually telling us what this thing is actually made of. And so with a 300mm lens, you can take a picture of a star that went supernova thousands of years ago, and you can tell what it's made of. That is pretty amazing that you can do this from effectively your back garden. This is one of the only images I'm showing which actually had a filter. It's called a tri-band filter. Tri-band simply means it lets through 3 particular wavelengths, and it lets through the wavelengths corresponding to the red of hydrogen, the blue of oxygen, and another hydrogen wavelength. That simply makes it easier to suppress any streetlights that happen to be contributing to your image. So the idea of using filters is sometimes it can help to let through the colors you want, but to suppress the colors you don't want. So some filters can be used to help in astrophotography, especially in more light-polluted areas. And this was taken from my front garden, not far from a street light. This was about 10 meters away from an LED street light, which was producing a whole load of light, but the filter managed to get rid of most of that and allow me to see this supernova.
How far away from Earth is that?
That is approximately 5,000 light years away. This is one of the...
Hydrogen there and oxygen.
Yep.
It's a likelihood of it in water.
The hydrogen and oxygen, it's very little because they are separated. In other words, they are not so close that they would ever get together and form H2O. There's a whole load of oxygen floating around, there's a whole load of hydrogen floating around, but nowhere near the density that you would need for these things to find each other and make water. This is one of the closest star-forming regions that we know about. This is only 400 light years or so away. It's called Rho Ophiuchus, and it's one of my favorite targets just because it's so colorful. And again, it's a reminder that with a color camera, you can pick up colors in the sky. Your eyes are not good at seeing these colors, but the colors are there. There's a little bit of pink at the bottom. There's a big star here that's making this area glow orangey yellow, and there's a blue star, a triple star down here that's making this region glow blue, and there's a lot of reflected light as well. So there's a lot going on in an image like that. Notice that this is only a 135 millimeter lens. You don't always have to have a 300 millimeter lens. Some of these objects are actually so big, I probably failed to note that in the previous one, but this object is so big I didn't need anything like that. An 85 millimeter lens, a portrait lens, is enough to pick up some of these objects. Just because they're astronomical and just because they're thousands of light years away, doesn't mean that they are so tiny you can hardly see them. You do not need huge magnifications to see these things. Some of these objects are big in the sky. So in this particular case, a 135 millimeter lens, there's a big star there called Antares. It's the brightest star in the constellation of Scorpius, for those that are interested. There's a star cluster in the bottom left. There's a star there making that part of the nebula glow blue. And there's clearly a lot of dark stuff as well that seems to be blocking the light from more distant stars. So there's yellow nebula, there's blue nebula, there's dark nebula, there's all sorts of things going on. And I took this picture quite a few years ago, and I thought, that's nice, that's colorful. But then I had the opportunity to revisit the same object, thinking, well, instead of a 135 millimeter, what if I went to a 300 millimeter, obviously a smaller field of view with the same camera? Is it worth just seeing what I would get? Would I see any more detail if I went to a 300 millimeter lens and took a whole load of exposures of that region? And I was very pleased to say it came out nicely, but it comes out looking so abstract. This is all genuine, it's all real structure, it's all real color. And all you need is an exposure long enough to capture that all. So yes, a 300 millimeter lens to crop down into the detail. But again, this star is lighting up this nebula. There's some of this dark nebula as well, a very bright star just off to the bottom, off to the left. But the fact you can pick this up, the fact that you can do this with a camera designed to take pictures in daylight. Nikon and Canon and Sony and all these other people design and build cameras to take pictures during the day of weddings and kids and football and all sorts of other things. But the same technology, you can take pictures of clouds of glowing gas thousands of light years away. The fact that it still works and it's not just shredded in noise, the fact that you can take long exposures, in this case it was the equivalent of an hour's exposure, more than an hour's exposure, and yet it still works. The beautiful Andromeda galaxy, visible with the naked eye, visible with a pair of binoculars, with a 300 millimeter lens and a few exposures of 1 minute added together. You see not just a fuzzy blob, you can see all sorts of structure within this spiral galaxy. It has a couple of neighbors as well, a couple of satellite galaxies, as well as the main galaxy itself. Hundreds of billions of stars in one galaxy system, a little bit like our own Milky Way. This is our nearest neighbor in terms of a big galaxy. It's only 2.5 million light years away. But it is our nearest neighbor because if you wanted to, you could photograph more distant galaxies. Still with the same 300 millimeter lens, this is a galaxy cluster. These things are not just randomly placed galaxies. These galaxies appear to be in a chain, so-called Markarian's chain, because they are gravitationally bound to each other. Presumably they were born at the same time and they seem to be tugging on each other, and probably all of these galaxies are gravitationally aware of each other. They are all pulling on each other and keeping themselves together rather than drifting apart. These galaxies are more distant than the Andromeda galaxy. These are 50 million light years away. So remember, light travels at, well, 1 light year per year by definition. So if these objects are 50 million light years away, it means that the light from these objects has taken 50 million years to arrive at Earth and enter the camera. So the light from these galaxies left those galaxies when there were dinosaurs on Earth. And for the last 50 million years or so, that light has been on its way from those galaxies and eventually caught by the camera. that got me thinking, how far can we go? 2.5 million light years is right on our doorstep. 50 million light years is a galaxy cluster like that. Just how far can we go with a camera that's designed to work in daylight? I thought about that for a while, and I had the opportunity to actually do something about it in the summer of 2020. Remember that summer? COVID, lockdown, can't go to the pub and see my friends. So I thought, what else can I do? Stephen Hawking said, don't look down at your feet, look up at the stars. So I thought, yeah, okay, I can't do anything other than stay at home. So let me think about how far I could possibly photograph with my camera without using a telescope. So I set myself the challenge. I got my tracker out, put it again outside the front garden, in the same place I took the supernova image. So again, this is not far from a street light. It's in the middle of summer. We don't get much night, of course, in the middle of summer. There was about 2 hours of darkness, 2.5 hours of darkness between the end of evening twilight and the start of morning twilight in July of 2020. So I thought, if I expose for a couple of hours, is it possible to get a really, really, really faint, really, really, really distant galaxy? So I looked up in a paper, what's the most distant thing that I could hope to catch from England in July? I found a very distant galaxy. It's called a quasar. That's just a type of galaxy that has a very bright nucleus. And I looked up the coordinates and found that there ought to be a galaxy just here. This is a bright star. That dot in the middle is a bright star. But just top right of that star, there should be a very faint galaxy. And I wondered, can I actually photograph that without a telescope? So I took about 2 hours of exposures. Again, I never take one long exposure. I take a whole load of short exposures. That has the advantage that if some clouds come over, you can throw those away. If an aircraft comes through your field of view, you can throw that away. If Elon Musk's Starlink satellites come across, you can throw that one away. And even if you throw a few of them away, you're still left with a large number of, in this case, 30-second exposures. Added those all together, that gave me this image. So the question is, have I actually captured that very, very distant object? It should be just top right of that star. So this is the standard setup for me, 300mm lens stuck on top of this star tracker. It should be in the middle of that square. If I've got the coordinates right by looking it up from somebody else's survey who said, here are all the interesting galaxies, there's one that's there, it should be in the middle of that square. So I took a 2-hour exposure, and then the next day I added them all together and looked in the middle of that square, and what I found was the least impressive image you're going to get this afternoon. But that there, where the two red lines meet, that is a quasar. It is a very distant galaxy, and it's been caught by this particular exposure of the 300mm lens on the camera with no other optical aid, no other telescopes, etc. So most of the light from this distant galaxy, most of the light from this quasar has gone into 1 pixel of the image. It's a 20 megapixel camera, but most of the light has gone into that 1 pixel. I've artificially brightened it here, so you can see some of the neighboring pixels have also picked up a little bit of light as well. But essentially, this object is at the mind-numbing distance of 25 billion light years. The light that produced this little blob in my image has been traveling across the universe for 12.4 billion years. Not million, billion years. The universe is 13.8 billion years old. This light has been traveling for 12.4 billion years before it arrived. So in other words, the light has been traveling for 90% of the age of the universe. The light left this galaxy shortly after the universe came into existence. And for all of that time, it's been traveling on its way to my camera. It traveled for 8 billion years, even before the Earth existed. And then the Earth came into existence with the sun, and the light continued to move on. Life evolved on Earth, the light continued to travel. The dinosaurs came and went, the light continued to travel, and eventually the light made it to the Wirral, dodged a few clouds, entered the camera, and produce that dot. Because of the expansion of the universe, we know the universe is expanding. This object is so far away, it's actually moving away from us at approximately twice the speed of light. That, again, is absolutely mind-numbing. The distance is mind-numbing. How long it's taken the light to arrive is amazing. And the fact that this object is actually moving away from us because the universe is expanding at something like twice the speed of light. And yet it can still be caught by a Nikon camera with a 300mm lens without using a telescope. The technology that allows you to do that is staggering. Something you should never take for granted. We could not have done this 100 years ago, but now everybody, pretty much everybody, has the technology, not necessarily in their phones, but probably in their bridge camera or SLR camera or mirrorless camera. They have the technology that they don't have to worry too much about the fact there's always a little bit of noise in all these images. As long as you take a long enough exposure, it is possible to photograph an object on the other side of the observable universe. That means nothing is outside the grasp of your camera in that sense. The entire universe is at your disposal. Let me finish just with a few comments about taking pictures from Africa. I've already shown you last time a few images of wildlife photography. Here I'm simply saying that my interest in astronomy has been around forever. I've more recently become interested in photography, perhaps a few years after my interest in astronomy started, and I've always had some interest in wildlife as well. And my friends who've decided that we all have this overlapping interest, friends that I've developed from university days. If you're interested in wildlife, you might be interested in wildlife photography, so the green and the blue overlap. If you're interested in astronomy, well, astrophotography is an interest, so the red and the blue overlap. The green and the red overlap because if you're interested in wildlife, you might go with a pair of binoculars to see wildlife. Those same binoculars can allow you to do nighttime astronomy as well. And if you're going somewhere remote like Asia or Africa or South America, somewhere away from streetlights to see wildlife, you might also have beautifully dark skies. So these three overlap, especially if you go on safari, and that's where a sort of idea of wild astronomy comes in. So my mantra was, if you wanted to, you could watch and take images of wildlife by day, stars by night, sleep when you get home. I mean, there's no point in wasting holiday time, is there? So basically you can do both. But there is a little bit of a catch. A box like this works well if you can counteract the rotation of the Earth. So that means ideally you want to make sure this box is lined up with the Earth's axis, which is not so difficult when you've got the North Pole star sitting up there, Polaris, telling you where the North Pole is, which is why you have a little polarscope. An app on your phone will say, if you look through this polarscope, then you should see Polaris here if you've got it correctly lined up on the North Pole as accurately as possible. That's fine in the UK, but if you think about where the North Pole is, the Polaris is where the North Pole of the Earth, the axis of the Earth is pointing. So that's not a problem from latitude like here at 52, 53 degrees north. That means we can see the North Pole star, Polaris, and it's a few degrees above the horizon, no problem. But if we're on the equator, where is the North Pole star? Well, if you're on the equator, the North Pole star is on the horizon. And that means it's going to be hidden behind an elephant or a hill or something else. So it's actually a bit tricky to line up on the pole when you're on the equator. And unfortunately, our favorite haunt in Kenya is sitting there pretty much on the equator. So that's a technical challenge just to make sure it's lined up correctly. But it doesn't stop you taking nice images. There's one of our satellite galaxies, the Milky Way, in which we live, has a couple of satellite galaxies. That's one of them. Again, you don't need a humongous focal length here. An 85mm lens was all that was required to take a picture of one of our companion galaxies visible in the southern hemisphere. And if you want to take a picture of the Milky Way, you can perhaps tell from the little blocks in the corners, this is actually a montage of more than one image, a wide-angle image, 35mm lens. If you go out in the UK and look up at the Milky Way, you might think, I can just about see a patch of the Milky Way. But you don't appreciate until you go to a dark sky site how bright the Milky Way should look if you didn't have any light pollution. By eye, it is possible to see all of this structure in the Milky Way. You see all of these dark areas, you see all of the stars, you see all of these structures. You don't tend to see the color because, as always, your color receptors do not work in low light. You need more light. But of course, the camera will pick out the colors as well as all of that detail. In this particular image, we have a couple of interlopers. We have Jupiter and Saturn. And if you take an image like this, a few minutes exposure with a wide-angle lens, when you get it on your computer screen and look in detail, you find that you've also caught loads of star clusters and star nebula and star-forming regions, etc. All of these have been documented and catalogued. It might seem a bit odd because it looks like everything stops there. And you're thinking, why is all the interesting stuff in the top left? Why is there no interesting stuff in the bottom right? Until you realize that all the cataloguing was done by people in Europe, for instance, from France, and you can't see any further south than a certain latitude, a certain declination in the sky, and therefore the people who made these catalogues couldn't see this part of the sky. So yes, there's lots of interesting stuff there, but they just didn't catalogue them. And when you get images like this, if you wish, you can blow them up on your screen and see all of these interesting things by just comparing them with a star atlas or an app or whatever. So the take-home message is, if you're getting away from streetlights, if you don't get away from streetlights, you really perhaps have to think about using filters to get rid of the streetlights to take nice images, but software can help. If you are going to have a holiday somewhere and you're taking your camera anyway, of course you're taking your camera if you're a photo group. If you're going on holiday and you're taking your camera, if you're going to get away from streetlights, don't ignore the fact that the sky at night could be just as interesting a target as whatever it is you're intending to photograph during the day. If you decide to pack for yourself a star tracker, whether it's one you built yourself or one that you decide to buy commercially, you can end up taking fantastic images of the night sky for very little additional expense. Thank you for listening.